Hi, kids. All right, second part of modern physics. The second part of modern was really primarily talking about nuclear physics and what's going on in the nucleus and nuclear decay and that stuff. So that's what we're going to talk about. First thing you need to understand is what is a fundamental particle. Okay, so let's talk about that. A fundamental, or sometimes it's called an elementary particle, is a particle that you can't break down into smaller pieces. I kind of love the story of how an atom got its name, because the word atom, I think it's in Greek, means indivisible, which, because the scientists used to think the smallest thing you can have is an atom. You couldn't break it down, and then, anyway, yeah, you can break it down. But a fundamental particle would not be an atom because you can break an atom down. So what are fundamental particles? Well, a fundamental particle would be an electron. Electrons are fundamental particles. A proton is not a fundamental particle because you can break a proton down. A proton is actually made up of an up quark, a down quark, and another up quark. An up quark has a positive 2/3 charge. A down quark has a negative 1/3 charge. So that if you have two up quarks and a down quark, you get a positive 1 charge. Hence, a proton has a positive 1 charge. A neutron is also not a fundamental particle because a neutron is really a down quark, an up quark, and another down quark. Okay, it is a dud because if you have negative 1/3, positive 2/3, negative 1/3, you get, hey, it's neutral because a neutron is a dud. But you need to understand what a fundamental particle is. A fundamental particle is a particle that you can't break down any further. So quarks are fundamental particles, electrons are fundamental particles. Atoms not, protons not, neutrons not. Okay. Um, well, let's talk about the nucleus. So, how do we make a nucleus? Well, we got to put this stuff together. So, let's say you have a proton and another proton. Well, do those want to hang out next to each other? No, they sure don't. They're both positively charged. They're going to repel each other quite a bit. Well, if you force them to touch, okay, even though there's this electrostatic force trying to push them away, there is a strong force holding them together. It's called the strong force. Okay, and the strong force is stronger than the electrostatic force. That's kind of how it's got its name. But that only happens. The strong force only occurs if the two objects are literally touching one another. They don't happen on a bigger stretch than that. Well, if you're building a nucleus and you have too many protons there, what's going to happen is eventually your electrostatic force is going to overcome your strong force and your nucleus is not going to be stable. So it's going to decay. Well, so what do they do? Well, what do they do? Nature. So what happens is you add neutrons. So these neutrons are going to add more strong force without adding more electrostatic force, which is going to allow your nucleus to become more stable. Okay. Um, I'm going to introduce it here, and I may do it more later, although maybe I'll just do it now. Here's the thing that's pretty cool, though. If you were to type the mass of two, or not add up the mass of two neutrons plus two protons separately, and you get a number, well, the mass of two neutrons separately and the mass of two protons separately is going to be a number that's going to be bigger than the mass. This would be helium. This would actually be that. Okay. Then the mass of a helium nucleus. Well, what happened to that mass? Well, the mass got converted to energy. And this is the weird thing about this equation, that mass is really just a form of energy. So this mass defect, this change in mass, times the speed of light squared would tell you how much energy is stored in that nucleus, and it's called the binding energy. That's the energy binding those nucleons, the protons and neutrons, together. Okay, so it's called the binding energy. Okay, but again, how do you do that? Well, if you take the individual pieces and you add all their masses up and you get a number, let's say you get a number 8. It's not 8, but for our sake. And then you were to say, well, if I was to look at this, and I was to actually look at the masses, and what do I get? And let's say I get 7. Well, my mass defect would be 1, and you guys would have to include units, but you get the idea. And then you would plug that in here, multiply by c squared, and then you could get how much energy went into binding that together. Okay, that's called the binding energy. Okay. A couple of other things just to remember. On your periodic table, this is important. This is your atomic number, which is the number of protons. Okay. This is your atomic mass, which is the number of nucleons, which is the neutrons plus the protons. Okay. So that's why this would be helium nucleus, which is really important. This is also called, and we'll talk about this in a little bit, it's also called an alpha particle, for like alpha decay. But it just has 4 total nucleons, and there's 2 protons. It's helium. Okay, so but mass defect, strong force. Hopefully that makes sense. Strong force, just as another thing with this, I have my atom here. Let's say the red represents my neutrons, the white represents my protons. You can kind of see these two are repelling each other. Okay, but in my model, I have glue that's holding them together. That glue would represent the strong force. Okay, but there you go. Okay, let's talk about nuclear decay. If I was to add, here's a proton, there's a proton, there's a proton, and just keep adding tons of protons and neutrons, eventually I'm going to reach a point, okay, where my nucleus is not going to be stable anymore. Okay, and you don't actually have to have huge nucleuses either. This would be carbon 12. It would look like that. Okay, carbon 14 has 2 extra neutrons. Carbon 14 is not a stable nucleus. Now, it's not super unstable. It has a half-life of like 14,000 years. What does that mean? That means if you had 100 nucleuses after 14,000 years, okay, 50 of them would decay. Okay, but that's what half-life means. But if I have nuclear decay, there's 3 types of nuclear decay. The first one is alpha decay. I don't know why I can't spell alpha. And here's what happens with alpha decay. So let's say we start with some random element. That's my atomic number. That's my atomic mass. Well, if I have alpha decay, that means I'm getting an alpha particle off. What is an alpha particle? It's really a helium nucleus. So you're getting this helium nucleus here. Well, in order to get that there, that means my new element would be Z minus 2 and would be A minus 4 because this plus this has to add up. And then typically you're also going to get some energy that's given off. And sometimes this energy is in the form of like a neutrino or an antineutrino, but it's just some energy. Okay, that's alpha decay. So this comes off. You have beta decay. Here's what happens with beta decay. Beta decay, you have a neutron, and it gets converted to a proton plus an electron plus some energy. Again, this energy might be a neutrino or some other form. But this is the basic premise that's happening in beta decay. Yes, a neutron is a little bit more massive than a proton because you get this out of it. So if I was doing a beta decay reaction where I'm getting an electron, and remember an electron is this, well, that means in order for this to work, this would have to be z plus 1, and then this would have to be this. Which, in essence, what it's happening here, it would be like, hey, I have my nucleus, and this is now turning red. I still have the same number of nucleons. It's just that I have one more proton. Although I guess it would have to be this turns white because I called the white one the proton. But you get the idea. Everybody follow that? Okay, and then you'd get a little bit of extra energy. And then the last type of decay is gamma decay. And gamma decay is essentially the nucleus goes from a higher energy state to a lower energy state. Or if you like, a proton in the nucleus goes from a high energy state to a lower energy state, or a neutron goes from a high energy state to a low energy state. So really it's more like, hey, I start with this, excited nucleus, and then it's not excited anymore, and it gives off a gamma ray. And gamma rays have really high frequency, lots of energy. But this is very similar to, like our energy wells from before, except instead of being electrons, you would have neutrons or the nucleus there. Okay, and that's why it gives us such high frequency that. And I think that is pretty much all of nuclear physics that you need to know. So I hope that makes sense. We just to touch on everything again. Fundamental particles. We talked about the strong force and how that relates to the electrostatic force, and how there's this idea of mass defect, and how this equation is going to be important with mass defect to find binding energy. We talked about the different types of decay, and we talked a little bit about half-life. So there you go. Bye, kids.